we're excited to have Corrine Yap, who's going to be from Rutgers University, who's going to be talking about reconstructing random pictures.
Yeah, so thank you so much to the GSCC organizers for having me here. Everything I talk about today will be joint work with my advisor as well, Bhargav Narayanan, who's also at Rutgers. So the specific problem that I'm going to talk about, reconstructing random pictures, sort of lives in this general interesting class of reconstruction problems. So let me start by giving a little bit of background as to what's been done in that class of problems. So the reconstruction problem most generally asks, given a discrete structure, can we uniquely reconstruct it from its substructures of a fixed size? So the most famous example of this is with graph reconstruction, and in particular, what's called the vertex and edge reconstruction conjectures. So let me just give you an example of that. Suppose I have some graph G, and let's say it's this one. And maybe I label the vertices A, B, C, and D. Let me look at the list of all of its subgraphs that I can form by deleting a single vertex. So for instance, if I delete D, I get that subgraph. If I delete C, I get this subgraph. If I delete B, I get this subgraph. And if I delete A, I get this subgraph. And you can see the last two subgraphs are the same. I've just drawn them in slightly different ways. But the question is, if I give you just this list of subgraphs, can you uniquely reconstruct my original graph up to isomorphism? So we're not caring about the labels anymore. And the question more generally is like, given just any graph, any general graph, am I able to uniquely reconstruct it? Or is there possibly another way to put the pieces back together to get a different graph? And this is still wide open. There are some results, computer verification has told us some stuff about small graphs. Bela-Bolobash proved that asymptotically almost all graphs are reconstructible, but it hasn't been, sort of proved, non-asymptotically. This is a really interesting question, but it seems very difficult. So people have looked at other types of reconstruction problems. For instance, with abelian groups, you can ask the same thing. Can I take a list of its subgroups of a certain size, and can I put those together to reconstruct the original group? And that result can be applied to, or that idea can be applied to get reconstruction of other objects like geometric sets using groups of isometries, things like that. Another more recent result is about jigsaws, and that was something that my advisor, along with Paul Ballister and Bela-Bolobash worked on, is if you look at a jigsaw piece, you can think about it abstractly as a subset of Z2. I'm sorry, the integer lattice, not Z sub 2. And you can look at its four neighbors and give each of its four neighbors a color from some set. And the colors sort of represent the different sort of prongs that you could have on the end of the jigsaw. And again, the question is, can you put all these sort of pieces together to reconstruct the original picture? But not only that, they actually considered a random version of this. So instead of looking at a particular fixed jigsaw, they asked, if I'm given a random jigsaw puzzle, what's the probability that I can reconstruct it? So what they actually determined was a threshold for this result. So if my substructures are of a particular size, a particular large size, then I am reconstructible with high probability. And if I'm below a particular threshold, I'm not reconstructible with high probability. So I'm being a little bit vague there, but I'll be a little bit more specific when it comes to talking about random pictures. And so let me tell you about what a picture is for today. It's just a cute way of saying an n by n grid where each entry is a binary random variable. So for each entry, I flip a coin, and if it's heads, I put in a 0. If it's tails, I put in a 1. And why is this sort of structure interesting? Well, it can be viewed as a two-dimensional version of this problem that actually has a very tangible real-world application, which is the shotgun reconstruction of DNA sequences. So if you think about a strand of DNA, and you're interested in sort of sequencing that, then there are sort of practical or technological, limitations to how much of that DNA strand we can take a snapshot of at once. And so in the real world, you can only look at, portions of a certain size at one time. So the question is that if my machine is only able to take pictures of certain size subsequences, can I stitch them back together to get my original DNA sequence? And so that's sort of a similar flavor as to the reconstructing random pictures problem, where now we're looking at grids. But I'm simplifying it a little bit. I'm just looking at 0-1 grids. And now I again want to consider sort of the random version of this problem and look at, for what size subgrid should I take to guarantee reconstructability? So let me give you a more concrete example of that. Let's say that I have this random 10 by 10 grid. And by random, I mean I randomly generated it on Mathematica. And let's say I take k equals 9. So that means I extract the list of all the 9 by 9 subgrids. And I've marked this sort of purple entry so you can keep track of, if you want, which subgrids these are. And there are 4 of them. Can I put these 9 by 9 subgrids back together to get my original 10 by 10 grid? The answer is yes, because there are only so many ways you can fit 4 9 by 9 subgrids together to get a 10 by 10 grid. And because of the significant amount of overlap between these grids that has to happen, there's only going to be one way where the entries will all line up nicely. But if I then bump my k down to 4 and I look at the list of all the 4 by 4 subgrids, I have a lot more subgrids to consider. And it's not so clear now that there is only one unique way to fit all of these 4 by 4 subgrids together to get a valid 10 by 10 grid. So what I'm really interested in is, when does it switch over? When does it switch over from likely not reconstructible to very likely reconstructible? And the reason that we care about likely reconstructible rather than guaranteed reconstructible or guaranteed non-reconstructible is because there are always situations where I am going to be reconstructible for any size subgrid. For instance, if I have the grid of all zeros, then no matter what size subgrid I take, it's just going to be the list of all 0 subgrids. There's only one way I can put that back together. So that's why we want to say, sort of with high probability, we want to sort of not really care about those, fringe cases of all zeros. And so here's the main theorem, is that we found what can be considered an almost sharp threshold. So this is not a sharp threshold, and you can sort of see that because the 2 expressions here that I'm considering in my 2 different statements are different. But we found if I just use this notation, Rnk, to be the event that my random grid is reconstructible from its kdeck, then if I have a certain expression going to infinity, the probability of reconstructibility goes to 0. And if I have a certain slightly different expression going to 0, then I'm reconstructible with high probability. So for the rest of the time, let me talk about what goes into the proofs of these statements. So for the 0 result showing non-reconstructibility, this is a very basic argument. It's just a counting argument. We essentially take this probability, and it's at most the number of reconstructible pictures over the number of pictures in total. And then we just find an upper bound to that using a counting argument by counting the number of kdecks. It ends up being like a stars and bars argument. You could give it to your combinatorics students. So what I really want to focus on is this result showing that if a certain expression goes to 0, then we are reconstructible. And the interesting idea that goes into that is what's called interface paths. So what we really want to do is give an algorithm that allows us to reconstruct the grid from the deck of k by k subgrids. And we want to show that at each step of the algorithm, the probability that we fail, meaning the probability that we sort of go off and start reconstructing the wrong grid, tends to 0. And this main idea of interface paths, it's not something that we came up on our own. It's actually used, sort of in much more significant, more deep theory, I guess, that in percolation theory and in statistical mechanics and sort of these things called contour models. So we're really just using it as a surface level tool, but these interface paths can be applied in a lot more significant ways, I guess. So let me describe what these interface paths are. Let's say I have my original picture P, and I started reconstructing it according to some algorithm. And so I have this piece of my picture so far Q that matches this side of P. And let's say it's correct so far. So all of these are 0-1 entries, and these 0-1 entries match. Then my algorithm tells me, okay, let's put the next piece from our deck in some way. We give some way of choosing a next piece to put down. What could possibly go wrong? So one way this could go wrong is, let's say that I was supposed to put down this subgrid S with these entries. And what I put instead is this subgrid T with these entries, where it does overlap and has the correct entries in the overlap. But in this area that hasn't been reconstructed yet, it hasn't been determined by any of the previously placed subgrids, I have something wrong. So you can see that this is 1, 0, 0, 0, and this is 1, 0, 1, 1. So if I am able to continue reconstructing with this T here instead of this S, I will end up constructing the wrong grid. But what would have to occur, like in order for me to be able to place this T has to be somewhere in my deck. So it had to have occurred somewhere else in my picture P. And in particular, it means that there is some subgrid hanging out in P with these exact white entries. And we can calculate the probability of that, right? So the probability that I have those k squared minus k entries exactly is 2 to the negative k squared plus k, right? Because there's just a 1/2 chance of each entry appearing. And I can sort of use a union bound over all the possible places that this T could occur to get an upper bound on the probability of some subgrid being placed in this position that is wrong. And so the idea is that we sort of calculate this probability along long paths of what I call bad grids. So if we consider an L by K reconstructed grid, and let's say we extend it K columns to the right, then what I'm going to do is I'm going to look at all of the grids in my extension, and I'm going to mark the bad ones and the good ones. So the bad ones are the ones that I put there and were sort of consistent with what I had already constructed, but they're not what's supposed to go there. There's some incorrect bit inside that subgrid. And I just mark all of those with an X in the upper right corner. And all of the correct ones I mark with a check. And maybe there's other stuff going around that can be going on here as well that I haven't marked. And then I look at the path separating the good and the bad entries, which for this picture would look something like this. And then for each of these bad subgrids, I can actually calculate, as before, the probability of that bad subgrid appearing somewhere in my deck. And for each subsequent step of my path, I can calculate the probability of that step occurring conditioned on the previous things I've already looked at in my path. And so with sort of an extensive use of union bound, I can end up calculating the probability of my path. And then I can calculate just overall the probability of any interface path existing in this extended subgrid. And that is the expression that we end up taking and saying, okay, if this expression tends to 0, then with high probability, we don't have any interface paths, which means with high probability, we don't have any of these bad subgrids hanging out. So this is really the two main sort of lemmas that went into this result. We broke up the cases into whether the interface path begins at the corner, so meaning up here in this corner, so like this interface path, versus if it begins somewhere in the middle. So the interface path begins somewhere here. And for both of them, we're able to, sort of take this idea and use union bound again and give upper bounds to the probability of these interface paths occurring. And then we just apply this to our reconstruction algorithm. So this is sort of a vague statement of what our reconstruction algorithm is. We essentially we start with some K grid, and then we extend it in each direction as far as we possibly can. And our previous lemmas show that, if one of these steps fails, in particular 3 or 4, then we are able to find some interface path. And if we're able to find some interface path, well, we know the probability of that interface path existing. So then we can say that the probability of either of these steps failing, giving us the wrong grid in the end, tends to 0. Okay. So that is sort of in a nutshell, the proof of this one statement. And in the end, it just boils down to being more careful with all of these computations. So where do we go from here? Well, I mentioned that this is an almost sharp threshold, right? There were sort of two different expressions, one that goes to infinity, one that goes to zero, that gives us the two different statements. It'd be nice if we could get a sharp threshold, right? If we could get those two expressions to match. And if you sort of word it in the way of, rather than like this expression going to infinity, this going to zero, if you word it as the way I originally described it, as like bigger than this k, reconstructible, smaller than this k, not reconstructible, there is a gap in the two different k's we're considering. So you can also think about this as sort of closing that gap between those k's. And we feel like it's not just a matter of doing better than union bound, right? We throw away a lot in the computations with repeated use of union bound. And we really think that either it requires a more clever application of these interface paths or a different idea entirely. Just because if you look at sort of the different expressions that are wrestling with each other in order for this probability to tend to zero, then we don't think that you can sort of save enough in the end by just being a little bit more careful. Another interesting problem would be looking at this in higher dimensions. So as I mentioned, this is sort of the two-dimensional version of the DNA reconstruction. You could look at the three-dimensional version, right? Now you're sort of dealing with cubes. And you have subcubes of cubes, and it's not clear what an interface path would be in that sense. And so if you could come up with a clever way to use this idea of interface paths, then these arguments might hold, but you might need something different entirely. All right, so I'm out of time, so I will end there, but thank you so much.
All right, let's thank Corrine. That was great. Really cool talk. Anyone have any questions? One thing I'm curious about is, so you talked about how this would be used for DNA. Mm-hmm. So how accurate is this, like, 2x2, or like not 2x2, but two-dimensional grid as a trying to represent DNA? Like, does this work well, or do you have to adjust it a bunch when you're going to that perspective? So I don't know what the specific applications of this problem would be to DNA, just because my understanding is that the DNA sort of is purely a one-dimensional problem. And so I don't know that this particular sort of view of it has any direct applications. But I think that the sort of the one-dimensional version, the actual shotgun reconstruction, that was sort of solved. There was a few papers that sort of started off this whole study of reconstructing these types of objects by Mossel and Ross a couple decades ago. So yeah, I mean, I imagine that this is a very simplified version of sort of any real world thing that you would want to study. But I think that you would have to be, probably in any actual applications, you would have to go beyond binary, and you would want to look at like Q-ary grids or something. But I do think that these arguments could very easily be translated to that setting. But I haven't considered it myself. Yeah, it makes sense.
I have a sort of more speculative question. Mm-hmm. And I didn't want to ask it until everyone had their chance. So Caitlin Lean-Camper is, I don't think she's in this session, but she also gave a talk at the open problem session yesterday. And her open problem that she presented was, given an oriented matroid, whatever that is, if I only get partial information about this oriented matroid, what's the smallest oriented matroid that I can construct that that contains that partial data? And I see one of the special cases of sort of one of the things she does, one of the special cases is graphs. Mm-hmm. So I'm wondering if your jigsaw construction for graphs has a analogous jigsaw construction for matroids, in which case you would have like various components of a matroid, and you want to say, what's the I have like, that certain things are independent sets of your matroid, and you want to know what the full matroid is that contains them or something like that. Have you looked at all about this?
I haven't but that sounds really interesting. So I have done a little work on matroids in the past, and from the limited amount that I know, it does. I think it would be an interesting problem to see if this would translate. I don't think anybody has done this particular type of sort of reconstruction problem with matroids.
No, but I think it's interesting.
Yeah, yeah. I agree. I have never thought about it before, but that's a really interesting problem. Yeah, thanks.
If you solve it, tell me the answer. It would also be interesting to know, just because there's a lot of, okay, I'm gonna say one more thing, which is, and then I think we have to leave probably for the thing, which is that there's a lot of connections with matroids and like linear programming, and people care about this when they talk about polytopes. And so this like has these connections to real world data questions. And so it would be cool if you could say, these are the pieces of data that I need in order to reconstruct some like data set.
Yeah. I think another sort of application that I didn't mention is that with the graph reconstruction, that can be applied to brain mapping and neural networks, because we have the similar sort of problem where you can only map certain size portions of the brain with one sort of snapshot. And so I imagine that there is a wealth of sort of applied problems out there that use these types of results that just haven't been thought about yet.
Yeah. And I think like specifically like some of the stuff that the people who have come out of Caitlin Leankamper's group are working on is neural codes.
Okay.
And that is their motivation. So I think Anne Shu is someone who like, she's at Texas A&M, so she's not in that same group, but she is someone who's like very like, it looks so connected to what you're doing.
Yeah. Okay. Wow. I didn't know about these. So yeah, thank you so much. I will look into that.
Well, let's thank Corrine again, along with Gabriel, both great speakers.